Hi, Ian. Hi, Jason. How are you?
Good, Professor.
Um,
Yourself?
okay. It is our last lab. I know. I'm just glad. Well, if I can get through tomorrow, it'll be great because I have meetings all day tomorrow, and then I have to present at Guided Pathways Summit tomorrow. I hope everyone's doing good. We got just 3 of you right now. Oh, physics. I was just talking to another student earlier about physics class. Yes, he stopped by office hours. Yeah, I took physics for A, B, and C at UC years ago in the 90s. I I after I graduated high school, I went to UCR, and I started with the life science major, and then I changed my major throughout. But yeah, I remember those days. Physics is pretty fun though. It's hard, but it's fun. Yep, I think so. Yeah, after I took physics, I took class like mainly, I see, I did calculus 1B, 1C, linear algebra, differential calculus uh, at UCR because when I tested in, I didn't have to take 1A. Then I took all the requirements like English and social studies, stuff like that. But yeah, I liked physics. Over there, they have great labs. They have labs that are pretty cool, but you work in teams. I remember we strap balls and things and we fling balls to the wall and we measure stuff. And uh, yeah, there were a lot of really cool stuff in physics class. I remember years ago. I finished in 1999. So that dated me. So because I started in 95 and I completed my bachelor in 99. And then I worked for 2 years. Uh, and then I went back to get my master's. Actually, no, I worked longer than that. I got my master's later on, but I took some time off and I worked. So it's exciting. You guys are going to be finishing down the line and get jobs, and it's so exciting. Life starts there, right? But when you're done with school, it feels great, you know, and then you can go for graduate school. I highly recommend it down the line. Find a company that pay for you to go to school. Okay, so check out the lab in Canvas and then we'll talk about the lab. In the meantime, I'm going to go ahead and open my editor and my simulator. So hopefully I won't have internet connection today, problem today.
Oh, hey, Professor.
Hi, how you doing?
Good, and yourself?
I'm okay. Yeah, yesterday was rough. I started at 8 and I finished at 8 p.m. So, um, yeah, still feel like so behind and work. So, but I'm good. Thank you. Thanks for asking. How's your class? How are your classes going? You're doing good this semester?
Somewhat trying to keep up with everything going on right now, especially like with COVID and that. Just gotta manage.
Yeah. Yeah, we had a high school student in the advisory committee meeting yesterday. She was helping us taking notes. She's like a middle college student. She was telling us how rough it is for high school students to do online. And there were some high school teachers there listening in. Um, and yeah, we like to get feedback like that because sometimes it's it's just different for from a faculty perspective with student perspective. Like when I write my lab, sometimes I think about like how the student would see it, because will they be able to do the steps? So I write down all the steps otherwise, and then I walk the students through it, but not the same for everybody. Sometimes people just give you the assignments and they say, here, do it. And sometimes that could be really hard because it's hard to understand what you're trying to achieve. um, okay, so we have 6 o'clock now. Okay, let me get my thing open. We're gonna work on a number generator today. Before we start, you have any question for me?
Professor, when you're going through the code, do you mind explaining when you fill with a location versus the number?
Sure.
Okay, thank you.
Yep, no problem. Okay, so let's go into screen share. Um, I posted an announcement just like maybe a few hours ago. The dean wanted me to let you know that Karma Thing is available for
Damn, she was just
And
saying
your internet's out.
about lagging out. Uh,
Sorry, I got knocked off of Zoom because my internet issue, but I brought out my hotspot, so just in case. It's just frustrating.
I
Just
can
to get
imagine.
internet connection at 7 p.m. And in the household, we don't right now, like in my house, we're not really using very much. But anyway, it's just so crazy. I have a hotspot that I use to travel when I do security work. Um, so I brought it out today just in case. So crazy. All right, let's go back. Okay, so anyway, we check out the announcement if you're interested in doing the karma thing. If I see other opportunity, I post it for you. Hopefully I'll have some time down the line where I will post some internship for you, but please don't wait to do internship down the line. Every summer is a really good time to just do some internship with big companies. And for computer science and computer engineering, there are tons. So if I can find them, I'll put them on the list, and then I'll include it with your Canvas. Okay. Okay. Yeah. Thanks, Eric. Yeah, I haven't had time to give him a call, but it's just this time right now. I know that we use, even though it's not dedicated, so it's always gonna floor me every time about like 6 to 8 o'clock. So, but anyways, um, let's.
Oh, Professor, in the Canvas page that you posted,
Uh
um,
huh.
there was a part of it that was skipped out, like there was no lines for it.
Let me double check Canvas right now. When I copied the picture earlier, um, I made sure I checked the lines. So let's see.
Maybe it was just a blank line then.
Yeah, no, it's just there was a little bit of a highlight from the previous line. That's what you see, right?
Sort of, yeah.
Okay. Yeah, it's just it got a little bit mixed in with the rest of the image, but I checked with the line, so we can double check right now. So this is going to be our last lab next Thursday. You're not required to attend the session unless you have questions. I will be available on our regular Zoom session. If you wanted to run ideas about your project, just keep in mind that everybody gets admitted. There's no, it's not like office hours where individual students can come in, and I would admit them individually. So if you wanted to stop in, you and your group, and just to kind of chat about your project or something like that, we can. I will be available until about 7:30ish, or even 8 o'clock if it runs longer. So it just be like, I will be on Zoom in case you have questions. Okay. And then, yeah, so you see a little bit of like the cutoff with the image like that. That's okay because it's actually part of the last one, like this one. But everything should be there.
Where there's the skip, there's not supposed to be a line right there. Where it says location of start of empty stack.
No, yeah,
Oh,
that's just a line for comment.
just making sure.
Yep. All right. So let's talk about our lab. I had previously opened it, but so you guys are doing one lab ahead compared to last year. Usually right now they're still at lab 9 because when I started last year, I was still on campus for the beginning part and then we transitioned to online. So we did one lab that was physical to gates. So that's a little bit different from last year. But, oh gosh, okay. So today we are doing a random number generator. Let's take a look at the actual lab requirement before we start the coding part, right? So in this one, we are using the linear congruential random number generator, your LCRNG, and it's an equation that we would apply very similar to what we've done last with Zeller. And in this one, we are going to use mod. Okay, so your input would just be the starting seed, and the integer can be in the range of 1 to 32,766, and that will be found in location hex 3100. When the program is executed, it's going to give you 20 random numbers in the interval, and so that's going to be 1 to 2 to the 15th power, and -2 were generated, and that's going to be shown. So the equation that we have is x of n is going to be a times x a times x of n minus 1 plus c mod m. And so we would need to multiply constant a and then constant c, and we would need to do mod m. And so that kind of bring back to what we've done in the prior weeks with multiplication, right? And then mod, okay? Now it says that m are integers that are chosen and fixed. So these, the c and the a are going to be constant, and with the mod, that's going to be integers. So if we are going to seed at hex 0, a random number sequence is going to generate it as in x1, x2, x3, x4, x5, and we should generate 20 numbers. What the x of I is going to be the range of 0 to m minus 1. And so eventually our sequence will repeat itself because this is pseudo random, not true random, okay? And in most cases, that will be desired to be the period of repetition as long as possible. So we will have subroutine with multiplication and division and the division is going to apply to the mod part, as we talked about in the earlier labs. So when we write this program, we have to consider this criteria. So then when you do x mod q, you would have to apply x mod q, and then you would multiply that by the constant a. That's going to subtract r times x divided by q if it's greater and equal to 0. Else, the condition for that would, the test requirement would be x mod q minus r times x divided by q plus m. So keep in mind that we have to incorporate this into our program, and q would represent m divided by a, r is equal to m mod a, okay, which brings us back to this, okay? So that's just division symbol. So here it says that to ensure no overflow while performing the computations and given the equation 8.3, multiplier a and modulus m must be chosen so that 0 is less than and equal to r and r is less than q. Okay, so we have to think about this. Okay, so your pseudocode, with the algorithm iteration, we would have x is going to be a times x mod n using Shrage's method. So then what you have is you are going, if you're looking at a, we would have like a constant. So in this example, what you have is you have a that's going to be storing 7. And so this is a multiplicative constant that is given. Then we would have 2 to the 15, which is 32,767. That's going to be loaded into m. We're going to subtract 1. That's the modulus is going to be given. So for the m, that's going to represent 2 to the power of 15. And then if we have an x, that's going to be your seed. Okay. So the seed that will be given. And then your q is going to be m divided by a. And then your r is going to be m mod a. We have to implement a for loop. And it's going to start at 1 to generate the first number. And it's going to go up to 20. So we would have to use iteration for this. Then for x, we're going to then apply the equation. And if x is less than 0, then x is going to be x plus m, output x. So it's going to return there. Okay, so that's how we're going to be able to generate your random number using Shrage's method. Then we know that we have to apply the 16-bit arithmetic, and for the 2's complement, we would use LC3 in the case that it's possible. So in when you generate random number, you wanted a large range, so that way it would give you variations in that range in the increment of 20 numbers each. So all the integers is going to be between 1 to the 2 to the 15 minus 2. That will be generated as the sequence, and in that you would see that it repeats itself because it's going to seed at the same position every time. Okay, so now we would then see that the random numbers one can be chosen as a is equal to 7, where that will be constant, and it's going to seed as x of 0, but this should never be 0. It should be any number that is above 0, right? Like what we saw earlier. Now, if it's going to be this, then it's going to be x plus m. So we want it to be in between 1 to the 2 to the 15 minus 2, which is equal to 32,766. Okay. So this little snippet kind of show you how the program part of it should be. Okay, so when you do the out command, that will be trap21, and it would output a single ASCII character found in 8 least significant bits of R0. So you can use out. We use puts quite a bit for like strings and things like that in the past. So you would then use out for this one. So in displaying the decimal digits for the register, in the case that it is negative, we wanted to indicate the minus sign, right? And with that, we have to ASCII convert the offset, okay, as what would be here. So the minus sign is going to be hex 2D, and the offset is hex 30 for 0 in ASCII. So that will allow us to show the negative sign in decimal, this part. In the next part, it says that to output the decimal digits of a number 1 by 1, we can obtain the digits by successively applying mod 10 to the number and truncating until we obtain 0. So in the case where we would need to produce the digits that are more than 1 digit, we have to consider to use mod 10 to represent, right? From the right, you have a single digit, then you have the 10th, the 100th, the 1,000, and whatnot. Okay, so the example that we see here is that when we would use, if the number that we like to output is hex 219, which is equal to 537, by applying mod 10, we would then be able to obtain 735. And you notice that it would be like this. So you would have to because it's going to be on stack, then we would push the 7 last. Okay. Then, so it would have 735. Now, when we have to output them in reverse order, then we can use the push pop stack to output it, right? Because we have to show the 5 first. So to implement this, we would say that the left is going to be n, and the sign of n is going to be 1. In the case that will be negative. If n is less than 0, then we sign it, just like what we did when we did multiplication, right? we would indicate that 1 in the front, because in binary conversion, that 1 indicates it's a negative value. And so we want, once we sign it, we would show that that will be negative n for the left. If left is 0, then we would show 0 digit, and then we would push that digit. Okay. When left is not 0, then the digit, we need to mod it to represent 100 and 1,000 and so on. So then we would push it. So we need to mod it when it's not 0, mod 10. And then we would push the digit. So on the left, we would represent left divided by 10. Then if sign is less than 0, then output the negative symbol, okay, to show that it's a negative number. And we wanted to check for empty stack, right? So while not stack empty, do pop digit. So if it's full, then we wanted to pop it and then output the digit. So we want to clear the stack. So make room for the next round, right? So any question with this? Okay. So when you
But
deal with,
Professor,
yes.
um, so when we're pushing the digit, it's like we're changing the value of it, and then when we pop it, it's like what's it called?
Well, you have to push it onto the stack so that way, because you use it as a storage temporarily, right? And that storage is used for operation. And when, you know, the compiler does this. So when it compiles your C++ program, what it does, it creates that stack, and then it's gonna bring in the values that you assign to your variable arrays and so on, and it uses it. At the end of the program, when you return 0, it clears the stack. Okay, so what we're doing is we're bringing in the digit. Let's say we operate and we calculate the digit. We need to push it on there to keep it there, so that way we can convert it and display it in the right manner, like, you know, in reverse. So if you have 537, 735 is pushed onto the stack, then we would swap it around and then display it. But we have to display it using mod 10, so that way it would display it, you know, left, second, and third digit. Okay. Once we've done that, we clear it. Okay. We pop it out. Okay. So we would use stack temporarily to store and allowing us to show multiple digits in decimal. Okay, so when you think about your project, when you're doing the grade calculator, or even with the sort, okay, you can think about how you would use the stack, and also bringing in the concept in that, you know, in the grade calculator, we have to sum it and an average, some, you know, and so on. Then we have to think about how when we sum our points, that's going to be a larger value, and then when you average it, and so how you can display that and use the stack effectively for your project. Okay, now we want to check for the stack to see if it's empty or not. If it's empty, we push. If it's not empty, we pop. Okay, and the computer does that. It you know, so when we look at the compiler, if it's not there, right, it's gonna bring in the value, and then after it uses it, it's full, then we want it to clear it, we want it to pop it. Okay, so the stack here, it talks about it's important, and the way that we would use this for this problem is that we would then push pop and use the empty subroutines. Okay, and so when we push, the content can be pushed to a register 0 onto the stack. So we bring it into the register and then we push it onto the stack. Then we pop it from the top of the stack in register 0. Remember, last in, first out. So whatever the value that will be last in, that's going to be the first one that's going to pop. Okay. So when it pop, it's going to pop from the top of the stack in register 0, and then is empty. If empty, returns 1 in register 0. If the stack is empty, it's going to return 0 if the stack is not empty. So if it's empty, it's going to return 1, and if it's not empty, it's going to return 0. Okay. Register 6 is going to point to the top of the stack. Remember, we talked about that in the lecture. So that's going to be our little meter, right? R6 is going to check, we're going to use R6 to check to see which value is on at the top. So that way we can pop. And so in R6, we're going to initialize to the location 4000, which is the base of the stack. So when you use stack, notice that your memory location is further down compared to your input location like XY, okay, which is earlier on at 3100. Because remember that in a system, when you're looking at the memory, there's a section of the memory that's going to be dedicated for things like this, like a stack. So manually, what we can do is we can point to that section, which is 4000. And by practice for assembly, that's what you do, is you don't want it to, mingle all of everything in together. It's not a good practice, okay? So we wanted to use a section that's further down. That's going to be our stack. That's going to be 4000. So that way it's not going to be overwritten as we change it, okay? Then R7 is used to store the return address when the subroutine is called. And we talk about that, right? Earlier on, like maybe 2 weeks ago, we talked about R7, how R7 is used in different areas. And then always is empty should be called before proceeding to the pop. Okay, because you have to check to see if it's full. If it's full, you pop, right? So if it's empty, you push. So that's a way that we can check it. And R6 is going to give us what's at the top of the stack. Okay. Now, to check whether the stack is empty, if empty pop should not be called. Okay. So your stack would be like this. In summary, this is not the detail. So you're going to have R6 is going to be loaded with the base. That's going to be the top stack point. So it's going to find what value is at the top with R6. We're going to call push subroutine. Okay. Then we have to stop that. Then we would fill the base at 4000 because that's our stack. Then for the push section, you're going to use R6 and you would do a -1 to move the top of the stack up. Okay, like as you push it, it's going to go up. So you have to subtract 1. Okay, and then we're going to store it. So store R0 there because R0, remember, that's how we're going to push in the value. And then we're going to return. When we delete it, we're going to pop. And again, right, as we store and push, we're going to load and pop. It's the opposite. You see? So when you store here, you got to load and pop. And so we would then load the top of the stack, right, which is from R6, what value that is, and it's going to bring that to R0. And then we're going to move. Earlier we moved down 1, so we're going to move up 1 back up to the top of the stack. and return. So if you think about pushing the coin down, when you do a -1, you push it down, there's a top piece. So when you pop, you have to take it up by adding 1. And then you're going to return. Okay. All right. Then for the is empty portion, you're going to load the label with register 0. Then you're going to add, right? We copy here R6, R0. We're going to add R6, R0 and put it on R0 because R6 gives us, right, the stack top, and then R0 is going to be the register that's going to bring in the stack value. And then we're going to branch 0. Okay. So here, if at the base of the stack is 0, right, then it's going to go here. It's going to clear it. It's going to add 1, right? Because we have to do the 1 for when it's empty and then 0 when it's not empty. Okay, so we have to add 1 here. And then for the following part, you're gonna have R0 is gonna be 0, so we put 0 here. For the stack is not empty and return. So this is the else, and this is when it is empty when you check with the if. Okay, and then for the empty, we're gonna fill it at C000, hex C000, which is gonna be negative hex 4000. As we fill the base, it's gonna be 4000. The empty is the opposite of it, which is negative hex 4000. Okay, so it's an abstract level of how we play with memory addresses, isn't it? Okay, so if it's empty, you subtract that, where if it's not empty, you have the hex 0. Any question? Okay, so here it gives you how the sequence of your random number should be generated seeding with the first x, hex x0, right? So you would see something like this, okay, and then the next value and the next value and the next value and so on in that range. So if we seed at decimal 1, right, that's where we start, then we would get the first x is 7. If we seed at decimal 6, we would have 42. If we seed at decimal 9, we would have 63, and so on for the next value and the next value. So it is a sequence, really. And if you took my CIS7 or you're currently in it, we talked about sequence already, right? So in this, what you have is you would have a sequence of 20 numbers, and you would have a seed that's going to generate the 20 numbers. Okay, so here it shows you how it would look like when you seed it at a certain value. So if I seed it at 10, right, my x1 is 70, and then my x2 is 490, and so on and so on. So this kind of gives you an overview of what it would look like with a certain seed value. Okay, so what I want you to do is I want you to write this program. I shared the code with you and we'll walk through it now. And then take screen capture of editor and simulator. And then you can test the program where A is 7. And then your M is the max, which is 32,767. Okay. In the equation starting with various seed. Okay, so if the first 10 random numbers generated in the case of that, it would look like what you just saw in that table. Okay, how would you adjust the program and display more randomly generated number? Okay, do your best in answering that question. think about what we're doing in the program. And then pertaining to the program, explain how the subroutines are used for stack operations. The reason why I state this is I want to make sure that you understand it so you can implement it for your project. Okay. Any question with this? All right, so let's look at your program. Did I close my editor? I had it. Okay. And you can refer to your lab page. I put the image there for you. So in this one, we originated at 3,000. So I had requests in how we would look at the fill. Okay. So just like what in the requirement document, we have to have a base that's filled at 4,000. Okay. And these areas are going to be the fill for the value. So your A and your M in your lab requirement at the end, we have to fill it with 7 and 32,767 decimal. That was what we need to test it with. So if you wanted to test it with another value, you can do a fill here. And that will be the same as the input. But what happened is when you fill it like this, it will be subsequent to the address, as the program runs through, it will just be at the address when you load that program. So when I load that program, it will be at the address of that fill line. So it's a little bit different than what we've been doing with the fill with the location for your, set value. That's a little different.
Yeah,
Okay.
Professor, because isn't A supposed to be like our time factor that would generate the random number? Or would that be?
No, because if you look at this right here, it has to be a constant using this method. Okay. Because if you have it as a set value, it's not a constant. Okay. This is a multiplicative constant that's given. It's a fixed value that they give us for Shrake's method. So you would have to apply this value. And also M is also a constant because that's going to be the end of your range.
So these would be more like set numbers, like you're not supposed to change them?
Yeah, so this one, when you generate the number, it's going to pull it from the range. But as it explained, it's pseudo random. There's no time consideration in this particular case. So because if you introduce time consideration, then you would then have every set of your numbers that you generated subsequently would be different. Okay. So it's going to seed at the same position as we hard coded in. Okay. All right.
Speaking of time, I suppose there would be a trap routine for that to get the time.
Yes, but if you do the trap routine with that, then you have to be able to, because then you would have to find ways to incorporate R7 in here somewhere. We didn't implement the time component in this one. Okay. So it's going to use that equation. It's going to seed at that position every time. Now, if you change the value, like, the 7 to something else, like what you see here, okay, if we modify it to, so it's going to it's going to be here, and at the end it's going to be at, that's why your M is going to be 32,767. But if you apply a different value, then yes, it does take an impact. It changes that. But in this one, it's a generator that's going to always see the same. There's no time consideration. Now, Ryan said that if you trap it, if you implement the trap, then we have to also include another subroutine that's going to work with directly with R7, because as R7, we would use this here to do what? To indicate, it's going to use it for puts, it's going to use it for return for some of the trap, and it's going to use it for, where is it? It's going to use it for the sign, for the negative sign. So technically, if you use R7 for the sign, then you can't have it trapped with R7 later on. Because when it stores out, that's where it's going to pull the sign from. Okay. All right. So here's the program. And I tried to comment every line for you, so hopefully that helps you. Okay. But you don't have to comment every line in your project. You can comment the section. Okay. So we load A and we load M into register 3 and register 2, or 2 and register 3. Okay. And then we're going to call the subroutine for the division. So coming back to the equation, we are trying to set this up right now. Okay. That's what we're doing. Then we're going to store R and Q to 4 and 5. So Q and R here. Then we are going to load X and we're going to load Q, and we're getting ready for the loop. So as you see, when you look back here, right, we're doing this right now. We wanted to do X divided by Q for if it's greater than equal to 0 for this part, but we also have to consider this. Okay. And then also this section is what we're working on. Okay. So we have to get ready for the for loop, and that's when we're entering the loop there. So with the loop, you have XQ, and then you call on the division because you have to do the X divided by Q. So we would store the product of X divided by Q to register 4, the output of X mod Q in register 5. Okay, following so far? Any question? Okay, then we're gonna load A to register 1. And we're gonna load X mod Q into register 2. As we store it here, we load it here. So we can now call the subroutine molt. Okay, so what am I talking about? Okay, well, you do have, when you look at the actual equation here, you have this and you have to multiply it by A. So that's why you have to do the molt. Okay, and you have this, that's why you have to do the division, and you still have to multiply it by R. So with that, we have to call the multiplication, so that way we can multiply it by a, and then we also need to load x mod q as we previously stored. So when we finish there, when it gets here, it's gonna, your R4 is gonna be a times x mod q. Okay. So that's handling what part, right? A times x mod q, this piece. Okay. Then we're gonna load R into register 1, and now we're gonna handle the mod part now. So that's, we're gonna load x div q into register 2. And again, we're gonna call on mult subroutine. So your R3 is then would have R times x divided by q. So as you know, right, we gotta take the 2 complement of R3 to do the subtract R like this, right? So we would then do the 2 complement of R3, and then we combine everything together and put it on R2. So R2 would have that equation. Then as R2 have the output from that equation, we wanted to check it for 0 positive. What are we doing there when we send it to skip? Remember that if it's greater and equal to 0, right, 0 or positive as the output for this, then we're going to make it go to skip. Else, right, it's going to go to a different section of the code. And that's how we write conditional statement. So then we would check what's in R2. If it's greater and equal to 0, we would send it to skip. Okay. Then we are going to load M into R1. And then we would then add R2 and R1 to put it back on R2. So as you recall, R2 has the complete equation, right? And then we simply add M, which lets us do what? This one. Okay? Any question? So now we take care of the otherwise section, right? By that point. So in the skip, you are going to store X from R2, the value from R2 to X. Now we are going to start with, it says the location of start of empty stack. Okay. So now we're going to check with R6. So remember that R6 is going to be our meter for empty or not, right? So we would need to load it with the base address, which is hex 4000. And then we would need to load X to R3. And this was what was asked of us in the lab document. Next, we're going to start our stack. We're going to clear R2. And we are gonna add 10 to R2 because we're getting ready to do the mod 10. So, and the stack, we're using the stack to do what? To push and pop the digits that would be divisible by 10, which is going to be your single 10th digit, 100th digit, 1,000 digit, and so on. Okay. So then we would call on the division subroutine. Then we would put R5. So we copy R5 onto R0 because R0 its job, what's asked of us in the document again, is to push. Then we're going to call on the push subroutine. And then we're going to copy R4 onto R3. So it's going to check what's in R3 for the next branch. If it's positive, then go to stack, else it's going to go to the next line. So if it's positive, it's going to come back here, right? And it's going to go again. Any question? Okay. So in the next one, I have an unstack. So we're going to call on is empty subroutine. We're going to branch positive and send that to cont, which is for continue. So if it's positive, it's going to go to cont, and otherwise it's going to keep going. Then we are going to pop. We're going to call on the subroutine pop. And we are going to also call on the decode, which is the conversion. So we ASCII convert with this subroutine, and then we're going to output. Now using out here, as you pull it from the stack, you're going to do one digit at a time. So that's why we're doing an out there. And here, this is an unconditional branch, but yes, you can use a jump. So we're going to come back to unstack again. So it's going to check. And if it's whether it should pop or not, right? So in the cont section, we're going to load label space to R0. And we would have it output. And we would load LC into register 6. And then we're going to subtract 1 as it tells us that when we move it up and down, right? When we move it, when we push in, we got to subtract 1 as it gets pushed down 1. And then we would then store LC. We would branch 0 positive back to loop again. And we would stop. So the way that I use space is actually the space for the digit to the left. Okay, which is space and then 10. Then your X is going to be filled with 100 in decimal. Okay. And then A, we were told to fill it at 7 to test in your program, right? We hard code this in as decimal 7, and M is 32767. Those values were given to us. Q and R, as they are arbitrary value to start, we initialize them as, I'm sorry, I should say arbitrary. We initialize them with the fill 0. So basically they start with 0. And then also these X div Q, we would also fill them with 0. The base is for our stack, so it's hex 4000. LC is for our loop counter. That's 20 because we have to make 20 numbers. And molt, for the molt, here we simply just clear R3 and then we send it with the loop. As long as it's positive, we're going to keep looping for M loop. So it's going to add R2, R2, and then -1. It's going to repeat as it counts down, right? I have to count it down as I loop through because it's one loop less. So it's going to keep adding until it gets to 0 and it would stop. So as long as it's positive, it's going to loop. And it's going to return. Then we have a division section. For the division label, we're going to save register. So save 1, register 2, save 2, register 3. We clear R4. We set up the 2 complement of R6. And next, we're going to clear R5. We're going to do a +1 to R4. We copy R3 into R5. At this point, R3 is going to be R3 plus R2. So R3 is going to, so what are we doing here? Anybody have any idea? Yeah, that's fine. Thank you. So in the D loop, that will be for the division loop, right? So it's going to keep looping and it's going to divide. And it's as long as it's going to keep going, as long as it's positive, it's going to keep going. And then we want it to stop at some point. So when it gets to 0, after 0, it's going to stop. Okay. And because we saved register, we would fill it with hex 0. And we've done this before. So when you save register, you just use hex 0. Okay. When you push, we push it down 1, right? So you ask, wait a minute, Dr. Wen. What happens here? We don't officially push until here, okay? And we're gonna pop here for the division. Now in the stack, if you look at the stack section, right, you call the subroutine, so you have to define that subroutine down here, okay? So for the multiplication, when you do all of that stuff earlier with the stack, when you call on that subroutine, you gotta set that up here. So we're using R6, right? So you're gonna add R6, R6 minus 1, because R6 is gonna be our stack indicator. And then we copy R6 to R0, as R0 is gonna be our main register that's gonna do the push pop. We're gonna return. Then if we store in push, we gotta load in pop. So we load R6 to R0. And then we subtract 1 up here. So we're gonna add 1 here when we pop. As when we pops it, it's gonna move down 1. So move up 1, right? And as we push it, it's gonna subtract 1 as it moves down 1. Okay, then is empty. We're gonna load R0 with empty. And we're gonna add whatever that's in R6 to R0 with R0 and put it on R0. And then we're gonna use R0 to check. If it is 0, then we're gonna send it to is. We would then clear R0 and then we would add 1 to R6 and return. So these two allow us to check to see if the stack is empty or not. Okay. And is empty is filled with hex C000, which is negative hex negative 4,000, as the stack is at hex 4,000. So when we build the stack, it's there, right? When it's empty, we gotta take it back. And then this just for ASCII conversion. And that is the end of our program. Any question? So as you can see, when you implement stack, there's quite a bit of a section that you have to make sure that you meter your stack, right? You check to see if it's empty or it's not empty. You gotta write the stack section, and then you gotta write the push pop section, which doesn't take very long. If you look, push pop is like tiny. Okay. And then with the stack, you just gotta start with giving it a base, and then you have it stack and unstack. This right here is just for us to do the loop counter with the output of our digits, you know, the 10, the 1, the 10, the 100, the 1,000 digits. So this is actually the requirement of the program after we mod 10. Okay. So after we write our program, click assemble, make sure that you check there's no error. Shouldn't be. I triple, quadruple checked this even before last year. Then after that, we're gonna use the simulator. We're gonna load it. Okay. So earlier I mentioned that, you know, when you load your program, you should, oops, see that. You should look at how it uses the address, right? And so as you can see, your address column is here, right? And the fill is here. So, and you can step through it. I think if you step through it, you can see it a little clearer, step by step. Okay. So now when you run this program, go to your console and voila, there is your random numbers. what if I load it again and run it again? Do I get the same number? You can check. Okay. Now let's see if we jump to 4,000, right? It knobs out already because after it puts the number, it clears your stack. Okay, so you won't see anything there. We mechanically implemented the algorithm to pop it out if it's not empty, so you won't see it there. So after the fact, after your C++ program, after you return 0, there shouldn't be anything there in the stack anymore. While it's compiling your program, yes, it's using that space to be able to get the number to the digits that what we need here. Okay, so now you can see how to output multiple digits in LC3 using one character at a time. Any question? Now, if you look at other example, you know, random number generator, this is not the only way to do it, right? And even using the same exact lab, if you look at, if I was to compare it with, you know, university students across that's using the same lab, you would see slight differences in how we approach it. But a big chunk of it is already given to us in the requirement of the program. They want us to use a certain register. They want us to use, you know, to do the stack a certain way. So I try to stick with what they ask of us to be able to do that. But yes. So you're out with the putc, right? Going back, I'll show you. I think we touch on this in week 8. Or maybe week 9, I'm sorry. When we talk about trap. So trap vector is different. Your out is output a character to the monitor. But getC, it also gives you, getC gives you the read character. So it listens to the keyboard where out works with the monitor or the display. I think you meant to say puts. So puts gives you more than one character. Okay.
I believe another difference is that
puts, yeah.
Yeah, I believe another difference is that without the character itself is in R0, but with puts, R0 has the address of the whole string.
Right, that's correct. So puts that's why you use the LEA with string when you're trying to get it to, because it's load effective address and you want to get that address to R0 when you do the put. Now with the out, you do the out one character at a time, and the way that we were required to do that, so we have to be able to do that. So now if you generate it as a string, then it wouldn't be integer. Okay. So we wanted to keep it as integer, so we use out. Okay, no, putc prints one as, yeah. So the difference between putc and puts is that putc, just like the getc, no echo. So that's because with the putc, it doesn't, it puts whatever character is in R0, where if you do the out, right, it's gonna do, so for the out, it's gonna pull that from R0, where with the putc, it's gonna pull that from the address. Putc prints one ASCII character in R0. Yeah, but it's gonna still find that from an address location with the putc. So what happened is when you look at your program simulator here, in that it's gonna have to move the address, right, into your MAR when it does that. Okay. So it's gonna take what's in IR and it's gonna put it into MAR in order for it to do a putc when it traps it. Other questions? Okay. So with this, what you have is you know how to use a stack, right? And then you know how to use push pop. And you also know how to do mod 10 to use, longer digits, integers.
Hey, Professor.
Yes.
When dealing with subroutines, they only work if you call them, right? Like either with a BR.
Yeah. Yeah. So the challenge that I see is that some students have in this class is to differentiate between a subroutine and a regular section of your code, right? So when you
Yeah,
use a
that's what.
label, yeah, so when you use a label, all the label, so when do we use label? We use label for looping. You see that? That's very helpful, right? You use label for subroutine, like a function, when you write a function, right? So in the C++ program, you would name your function, right? Like int calculate, for example, right? So when you do that in C++, it's like using a label calculate for your subroutine, okay? They are just identifier, okay? So if you can wrap your head about saying, okay, so if I declare a function and I start defining that function, well, I got to give it a name. And so when you do that, you just put a label to it. Now in assembly, right, it's just going to flow top down. All languages does, right? If you look at Python, it does that with the interpreter. Well, in assembly, we can navigate it. We can move it around by using label. Like, what if I don't want to do this now? I wanted to do it later, right? I can branch it. So you can have like different, you can write the entire program, but you can do the first part of your code first and then branch it to the bottom part of your code and then come back to the middle part. Okay. But it's gonna flow top down anyway. So if and it's gonna do something here and then so we can use label that way, and you can also use label in C++, Java, and all the C languages. You can use label. And this is where it comes from, is assembly. Okay, so we just identify a section of the code to do something. And for the function, that's exactly that, a section of the code to complete a task. So we would then have a section that would just do loop, and label is used, in various ways. We would implement loop, we can move it around, we can implement subroutine or functions, um, and so on. And you might have two section. One is for, if, and then one is for the else section, or the else will just continue if the if doesn't check true. So we can apply label for condition, iteration, subroutine. And the hard part is in C, you don't have a way to really, I mean, you can, but you don't really name your loop, right? You don't identify your loop. But in assembly we do. It's, can you just, how are you going to be able to keep it continue if you don't have a label there, right? You have to branch it, so you send it back. You can force it. If you have a while loop, you just force it to come back. You saw that last week when we did the other lab. Okay, so um I think, is it going to be matching 100% in what you do in C++ in assembly? The programming part, like not the syntax, the format, is they're different, but the programming concept is the same. Okay, you're still going to have to check for things that are true, but in assembly for LC3 you can only check 0, positive or negative with numbers, and that's it. Okay, so other questions, anything, any feedback, any concern you have? And if you look back in all the programs that we have done so far, right, and this is more of an advanced program, right, like you have stack and things like that, you came a long way. You didn't before, when you look at this, you're probably like, what is that, right? Like how the heck do I achieve that? But now when you read through it and you can understand it, that means that's definitely progress in my book. Okay, so the whole point in me going through line by line with you is to show you how to do it so you can do it.
The professor, with the subroutines, they don't work unless you call them.
Yes, JSR. Yep. So think about, so in this one, it's a little different than your C++, right? Because in C++ we call everything in main, unless you do recursion, then you call, you have, a function that calls itself, right? You saw that. Okay. So in this one, the way that we did this is we use the subroutine to accomplish the task when we work out the equation, right? So when you look at the equation by piece, right, you would need to do the multiplication here, right? And then you take care of that. Then you need to do the division here. So as you work from in outward, you're gonna have to, it's very sequential in that aspect. So after you have it mod, after you call the division here, you have to multiply, or you multiply x, and then you call the division for the mod, right? And then you multiply it again. So that's why you call the JSR mult, right? So that way you can handle the multiplication. So coming back to our code, right? This is why you see, because we're trying to do the division for the inside of the parentheses, right? You're trying to get to x divided by q. So you call the division. Then as we progress outward from the parentheses, then we would then call the multiplication, right? So yeah, here again, multiplication. So if you think about, oh, well, in C, I just put it in the main and that's it, right? Assembly is step by step, right? It cannot get to the next part until it achieves, so it's very sequential in the way that you do things. So when you get here, right, in order to get to the next step, you have to get the result here and then go to the next step and then get the result there and then go to the next step. Okay. So now you have learned how to have structure in your program with stack. That's great. Yeah, I like assembly. I think it's I know it's tedious, but it reinforces a lot of the programming concept on how you would use subroutine or functions, how and so on. Any questions? Okay. So we created the program, take the screen capture, answer the questions, and then submit it. Okay. So we still have lecture on Tuesday. Don't forget, we still have to cover a few more things before we wrap up. So this is week 10. I have lecture, and then in week 13 and 14 on Tuesday, I will cover, hopefully I can knock out, each part because they're kind of lengthy. So you can attend and do the final review. Yep, time to type in your name. And hope you have a good evening. I'll stick around for some questions. I'll see you next week. And start looking into working on your project, okay?
All right, see you next week, Professor.
Bye, take care, have a good night. Thank you.
See you, Dr. K.
Bye. Bye, Ryan.